just above the runway. So these sorts of things, and that was back in the days before we had helmets or parachutes or anything like that. So I was always a little cautious. All right, Peter Drucker, he's a management guru, no longer with us, but the man was brilliant in many, many ways. And I've been characterized as being one of these people. And I always tell them, well, then why have I been wrong so many times before? But Drucker says the important and difficult job is never to find the right answer. It's to find the right question. And until you've asked the right question, you can't possibly come up with the right answer. There are always a lot of people who can quickly come up with the right answer. But you have to frame the question correctly before you can get there. So this is a story about the minimum drag of wings. Now, there's an interesting problem here. And it turns out that there's a whole lot of history that happens before you can understand how we got to where we're at today. So let me see if I can't get through this. Now, one of the things you have to understand to begin with, very fundamentally, is where does lift come from? Okay, a lot of people think that lift comes from the downwash behind the wing. It turns out that downwash is not a necessary part of lift. If you build a wind tunnel model that goes from one wall of the wind tunnel to the other wall of the wind tunnel, and it's a wing, okay, but it doesn't have a wing tip. So it turns out that the airflow that comes in, and then it sweeps up, exactly meets the leading edge, then it comes down and leaves the trailing edge, and it comes back to the exact same level that it was beginning. In other words, there is no downwash. But the wing still produces lift. How is that possible? Well, it turns out, I used to wonder this, and it took a good friend of mine, a gentleman named Paul McCready, to explain it to me. And Paul explained that you get a higher velocity over the top and a lower velocity under the bottom. Everybody knows this. Bernoulli, this is where lift comes from. And the higher velocity, higher kinetic energy, it has to reduce its potential energy. And the potential energy is locked up as the pressure. And so lower pressure on the top, higher pressure on the bottom, you get lift. Paul then goes on to explain that you take a 747, okay? All of us are familiar with grand piano. You know what a grand piano weighs. It's about 0.6 of a ton, each grand piano. So you take a grand piano, and you know what the surface area is on the top of the grand piano. You then take a second grand piano and you stack that on the first one. Then you take a third grand piano and you stack that on the previous two. You now have the wing loading of a 747. It's about 80 pounds per square foot. Okay. Bernoulli makes enough pressure difference between the top and the bottom that 747s fly. We know this. We see it every day. So, where does that lift come from? The lift is the velocity difference between the top and the bottom. But in the process of creating that velocity difference, when the two airstreams come together at the trailing edge, and you do not get the two vertical lines that were at the leading edge, they do not meet again at the trailing edge. It turns out what happens is there's a horizontal rip in the air. And the size of that horizontal rip is the drag of the wing. And you now have the case where you don't have any downwash, but you still have lift. Okay. Every single one of you who understand what I just said is smarter than the editor at a very respected scientific journal that refused to publish my paper. All right. So it also results in, and you can see the circulation right there at the leading edge. You can see the circular motion of the air, of the fluid in this case. And you can see just behind the trailing edge, there's another one. And what has just happened here is that airfoil has just started moving, and it creates a startup vortex, and it gets left in the air. I've heard of people on certain days, on foggy days over at LAX, just as the aircraft rotates and starts to create lift, you can see the startup vortex start. And it just sits there as the airplane flies away. And there's this startup vortex that's left circulating just above the runway. So these sorts of things actually do exist. And everybody says, well, circulation, that's just a theory. It just makes it convenient. Well, there was a brilliant man who figured all this stuff out. I'm going to talk about him in just a minute. All right. Flying wings. Everybody gets fascinated by these things. But in many respects, they're actually very cantankerous. And they don't fly particularly well. It takes a lot of tuning in order to get them where they fly really nicely. And why is that? What's the problem here? And it turns out that every day we see a flying wing. These things. This is a wandering albatross. And by the way, up there on the screen, that's actually a little too small. That's about half scale for the bird. They're about 12-foot wingspan. It wasn't until 2012 that we actually figured out what they do 8 months out of the year. We knew that 4 months out of the year they come back to the place where they roost. And it turns out that the male and the female, they mate for life, and they form these long-term relationships, and then the male will go off and eat while the female sits on the eggs. The male comes back, the male sits on the eggs, and the female goes off to eat. And then when the hatchling arrives, they both take care of the hatchling, and they do one every other year. Okay. It turns out no one knew what they did for 8 months out of the year. So in 2012, a paper got published by a gentleman named Gottfried Sachs at the Technical University of Munich, and he finally figured out what they do. It turns out when they leave the nest, they fly around Antarctica, around the world, 5 to 7 times every year. By the way, we think these birds live about 80 years, and they reproduce every other year for their entire lives. The oldest known bird in the wild is an albatross. Her name is Wisdom. She came back about 2 weeks ago to her nesting place in the Hawaiian Islands. Wisdom is 67 years old. She has made 2 trips to the moon, and she's on her 3rd one now. That's how far these animals fly in their lifetimes. And we never knew this until Gottfried Sachs GPS tagged 20 of these animals, and 7 of them came back the following year. Sachs also figured out dynamic soaring. This animal is at the bottom turn of a dynamic soaring maneuver. It's pulling 3 Gs. So this 20-pound bird has 60 pounds of load on its wings. Look at the feathers at the wingtips. They are not bent up. This tells you something about the load that's on that feather. So I want you to think about how much load you can put on the tip of a feather. You would measure this, what I'm doing right now, in grams, okay? We're not even talking an ounce out here at the tip. So those feathers at the wingtip have no load. Okay. There were a couple of brothers about 115 years ago, 118 years ago, that figured out, you know, this flying thing might be really interesting thing to get into. So they built a kite to demonstrate an idea they had on how they might be able to roll an airplane. And the kite actually worked really well. So then they built a couple of gliders, and the 3rd experiment that they did was the first glider that was big enough to fly. So Wilbur and Orville went in 1901 to Kitty Hawk, and they started flying this glider. You'll notice there's no vertical tail. They've been looking at birds. You don't need a vertical tail. And so they didn't put one on their glider. And what they found out was this ugly thing called adverse yaw. Now, I know we have a lot of pilots here. Pilots, the one thing that pilots have that normal people do not is they know what to do with their feet with airplanes when they try and turn. This is the fundamental skill that pilots understand and know. And I can remember my instructor in the back seat of a Blanik L-13 sailplane. Every time I didn't use my feet correctly, he had a roll of paper that he had stuffed in the side pocket, and I'd get on the back of the head every time. I can still remember this. I was 14. I remember. Okay, so it turns out that Orville gets very frustrated because what happens is the airplane has huge amounts of adverse yaw. This glider down here from 1901. And the adverse yaw sets in and the airplane starts flying sideways, and they can't recover the airplane until it crashes into the ground. They leave camp in the morning with enough parts to rebuild the glider 5 times. And when they're all done with their parts, it's time to go in and have lunch. That's how bad it was. So they go home very, very frustrated, and Orville tells Wilbur that man would not learn to fly for 50 years. He was convinced this was an unsolvable problem. But he goes back and he makes a wind tunnel. And they test 700 configurations, 2,000 wind tunnel runs. There is no luck at all in what they ended up doing. These two brothers worked incredibly hard on this solution. And in 1902, they come back. Their entire flying season in 1902 was from October 10th to October 26th. 16 days. That was it. On the 26th, they take 2 photographs. By the way, Wilbur and Orville took thousands of photographs, and 319 of them still exist. And they were documenting their entire process of how they learned to fly with photographs. Now, there are claims, and this just raised its ugly head again a couple weeks ago, of people who flew before Wilbur and Orville did with powered airplanes. Don't you think if you were the first person to fly an airplane successfully, that even if you crashed at the end of the first flight, that you'd go out and take a selfie or have someone take a selfie of you standing in front of your wrecked airplane that was successful? Those photographs do not exist. The only ones who have photographs of such a thing are Wilbur and Orville. And they had every single step all along the way. And that's why we have this amazing documentation of the experiment. So in 1902, October 26th, they take 2 photographs, both of them from the back, both of them of the glider in a bank. You'll notice that the left wing appears fat and that the right wing appears thin. This is their wing warping. And this is how they were able to bank the airplane. You'll notice they've added a vertical tail. The vertical tail actually is a rudder. It's coupled to the aileron. Okay, the reason they took these photographs, this was the day they knew they had solved the problem. These are the first 2 photographs of a heavier-than-air air vehicle in coordinated turning flight. Because they quit flying on this day, and the next time they come back, December 17, 1903, in the upper right, Wilbur and Orville fly the first airplane. And this is the day that we always celebrate. And the reason was because of that glider. And when they patent the airplane in 1906, this is the drawing in the lower right of their patent. And you notice there are no propellers, there are no engines. What they patented was the control of the airplane, not on the fact that it was powered. This was that important. And so everyone since then has needed some direct method of yaw control. A rudder is the easy way to do it, but you could also create drag at the wingtips in order to be able to fly aircraft. But along the way, we didn't have a good explanation of why that needed to be until this gentleman came along. And this is the guy who figures out how wings actually operate. His name is Ludwig Prandtl. He published a paper in 1920. It would not be for another 12 years that the British would accept what Prandtl had come up with as the explanation for lift. But the amazing thing was that for the first time, you could change the incidence of the wing and you could calculate what the lift change would be, or could put a control surface on it, or a flap. This was the first time that you could actually calculate what the lift would be without going into a wind tunnel and figuring it out. If you change the aspect ratio, if you change the span, all those things suddenly became possible because of what this man did. Once you have the tool, you can do optimization. That's exactly what Prandtl and his team of students did. And he found out that the elliptical span load was the minimum drag for a wing of a given span. Now, this is still true today. And if you have a span limitation, you have a T-hanger that's only 44 feet, whatever, this is the answer you should use. If you have a span limitation, all right. By the way, that is called a constraint. If you change the constraint, you get a different answer. And so one of the results of this is you get wingtip vortices. And the last thing you ever want to do is ask an aerodynamicist about, hey, what about those wingtip vortices? Because you will spend hours listening to the aerodynamicist tell you about wingtip vortices. All right. There are thousands of these photographs. Sometimes you can see the elliptical load from one wingtip to the other. This is the Concorde taking off. There's a photograph of an F-18. You can see the ellipse from the load distribution across the wing. Sometimes, rarely, you can get both. But somewhere along the way, in all this great capability that we were able to develop, we forgot about these things. They still knew something that we didn't know. How on earth do birds turn and maneuver without the use of a vertical tail? And oh, by the way, you've never seen a bird with a stall spin problem, have you? It turns out that all the aircraft that the way that we build them, many of them have really severe stall spin problems. Birds don't have this issue. And yet they have these very sharply tapered, they go out to nothing at the wingtip. Those tips should stall. And by the way, those feathers, they're sticking straight out. Why don't they bend straight up? There ought to be a huge load that disappears right there. And this is what the aero engineers keep telling the bird people, that you need an elliptical load on your bird. So Prandtl still thinks about this problem. He wasn't trying to solve the bird problem or anything, but he came up with a new solution in 1933. And he came up with an alternate solution, and it's that curve C up there that tapers off, the load tapers off to nothing at the wingtip. And if you think about this, the load goes to zero, all of a sudden, feathers sticking straight out at the tip. Makes perfect sense. Now, the new constraint here on this wing is that he called it integrated bending moment. Big fancy words. Engineers like to use big fancy words to hide what they mean. Let's talk about a Cessna 150, 152 for right now. All right, 38-foot wingspan, 2,400 pound airplane. The wing, if you unbolt it, is about 450 pounds. Imagine that we have 450 pounds of aluminum laying right here. Prandtl said, instead of thinking about a 38-foot span wing, he says, now I want to carry the same load, I want to carry the same G limits. I have 450 pounds of aluminum. What's the minimum drag I can get out of 450 pounds of aluminum? That's this new curve C. If you want to find the minimum drag for a given amount of material, this is the paper you should use. And in fact, it's 12.5% higher in L over D than the elliptical solution. Now, it's got a bigger wingspan. This is the thing you have to remember. If you have a span constraint, you want the other solution, that elliptical solution. If you don't have a span constraint, if span can be unlimited, then you want this new solution. And this is the part that we all miss. And I can tell you exactly how many airplanes have used that new curve C. The number is 8. And all 8 of them have been constructed in one particular place. That's not quite true. There's two places you'd have to go to in order to see both places where all these airplanes have been built. Okay, so here we have the original paper. By the way, it's 11 equations, only 2 pages. 11 equations, 2 figures, and 1 table. And Prandtl, second sentence says elliptical is not the right answer, and the last sentence here, he also says elliptical is not the right answer. It's only ever been published in German. We do have we have 3 English translations of this paper now. But the derivation, we've gone through the derivation. It is correct. There's 3 typos in this paper, by the way, that we found over the years. Prandtl is absolutely correct, but he misses some things here. He never actually goes so far as proposing it as a solution. He never references this paper. Only one person ever referenced this paper, as far as I know, before I arrived. And that gentleman was R.T. Jones, the chief scientist at NASA Ames. So, and by the way, there's a picture of Prandtl and Horton. Now, Horton did something very similar, but it was not exactly the same. Prandtl and Horton talking. I have 7 photographs. These are the best 2 that I have out of that particular day when Prandtl and Horton talked. Well, unfortunately, if you go through all of Horton's stuff, he never references Prandtl's 1933 paper. If you go through all of Prandtl's stuff, he never references anything Horton has. The 2 of them were talking, but they were talking past each other. They weren't exactly talking in a manner that they each understood the other person's position. And so they never solved the problem, either one of them. Prandtl had about 50% of the solution, and Horton had about 35% on the other side. And there was still about 15% that was missing. So one other place we have to stop is Dick Whitcomb. And Whitcomb was the guy that came up with winglets. This was in 1975. And I need to explain this to you. When you put a winglet on an airplane, you don't actually change the location of the vortex. The vortex still happens at the wingtip. But what that winglet does is it takes a little bit of energy out of that vortex and it pushes the wingtip forward. And you can see that down here in the lower right. You notice that on the left side of that it says minus little d, capital D. Well, that means there's a negative change in drag on the winglet. The winglet actually produces thrust. So if you cut the winglet and you put a load cell right there and you flew the airplane, you'd find out that the winglet's actually pushing forward on the wingtip. And this is the way that winglets reduce drag on aircraft. So now I want you to imagine that you make the winglet really, really big. And in fact, you make it so big that it's 30% of the span of the wing. And then fold it out flat. Now you want to put the entire aileron control surface on the winglet. None of it extends inboard. Now, I just told you that there's thrust on this winglet, and that's because it rotates the lift vector forward. So now if you increase the size of that lift vector, you increase the amount of thrust that you get out of that wingtip. So now if you wanted to lift that wing up by creating more lift, you would get more thrust. And in the process, you would not need a vertical tail. And this is what birds have known all along, and they never told us. All these years. So, winglets. All right, let's go through. This is the plan form that we decided to use, and in order to get that winglet effect, this is the twist that we had to put into the wing. Okay, it's very nonlinear, and the numbers are very large by comparison to what you're normally used to. Most of us are only used to using maybe 2 degrees, possibly as much as 4 degrees of twist in our wings in order to make them so they stall reasonably. We're using numbers like 12 or 16 degrees. I've even done a design that requires 20 degrees of twist in the wing. If you come over and look at our place and you stand on the wingtip and look down the wing, you can see how much washout there is in the wing. Okay, Oh, there's this whole problem of there's a sag on swept wings in the middle. And Horton ran into this. He called it middle effect. And flying wing people are used to dealing with this, swept flying wings. It turns out there was a gentleman, Dietrich Kukiman, who explained this. He was British despite the name. But he explained that the vorticity is shed where the two wings come together. And so there's a sag in the middle of the wing where you get the two wings coming together. And this sag is in the lift. And so you don't get as much lift. And so the vehicle ends up feeling like it's nose heavy. And so it turns out there's a way to overcome that. And I've been using this trick by changing the incidence of the wing through the center section. All right. We do use our elevons. We like more span further out. Again, you're trying to get you want to get away from that tip vortex and capitalize as much on the upwash out there at the tip from that vortex. So I calculated all this, and having been a sailplane pilot, I knew exactly what the rudder pedals were for, and I convinced myself that adverse yaw was a fact of life, and what on earth was I thinking that you could ever get proverse yaw? And I had a young man who was an intern working with me at that time. His name was Mike Allen. This was 1996, 1997. And Mike, by the way, he's not a young man anymore. He's in his mid-40s. Modeler, right? Modelers. And Mike took a standard Klingberg wing kit, and he put the twist that we had calculated into that Klingberg wing. Put an RC system in it, and we went out and flew it. And dang, if that thing didn't fly exactly the way we expected birds to fly. It was just unbelievable. And I mean, I abused this little glider like you wouldn't believe to try and get it to misbehave. And I could not get it to misbehave. It always went the right direction when it was trying to maneuver. So here's what we get. Downwash in the middle, you see the upwash at the tip on each end. In fact, if you could see the vortex and the wake, now remember, this is not real flow. This is just math, right? On a computer screen. It would look something like that. So you can see that the vortices are not at the wingtips. They're about 70% of the way out. And in fact, if you actually had an airplane that you could do this with, you might be able to see those vortices. And further, instead of those wingtip vortices being all the way out there at the tips, if birds did this, when birds would fly in formation, they would fly with their wingtips overlapped. And they do this. Now, we've studied many of the papers published by the ornithologists about the way birds fly in formation. And it turns out that our data lines up with their data exceptionally well. And so we started looking at more bird papers. And I had a team of folks that were giving me a hard time about this, and it was really difficult to deal with them sometimes because they'd come in with a new bird paper and say, what about this one? Answer this. And it's like, give me a week. You know, I only have one problem. I can only solve one problem at a time, and I am not particularly quick, all right? It turns out that there are lots of photographs of birds and the wingtips overlapped. So this particular gentleman, I always pick on this guy, and I'm going to skip over a couple more in here in just a minute. But Jeff Spedding. So Spedding was a PhD in zoology, and he got his degree in Bristol in the UK. He was, this paper was published in 1987. He got his PhD in 1984. Brilliant man, unbelievably brilliant. And I showed this to a friend of mine in 2015, and he says, Al, Spedding's at USC. And I go, no way. No one would do that. I mean, for a professor to move from one school to another, it's like hitting the big reset button and starting your whole career over again. And I mean, coming from England to the United States, and what would he be doing in Southern California? So this was very interesting to me because I lecture in the design class at USC, and so the next time I was down there, I hammed this one up pretty good, and there were 4 students in the back who were just aghast the whole time. And by the end of my short diatribe about this poor guy getting the wrong answer, these 4 students had to come up and introduce themselves. They were his PhD students. They said, we can arrange a meeting with Professor Spedding for you. But what he found out was, you notice he got this bird to fly through soap bubbles. Those soap bubbles were filled with helium, so they would be neutral buoyancy. And the bird would fly through this cloud of soap bubbles, and you could see where the vortices were. And he found out that they were 0.76 of the wingspan apart. But the problem was, he knew that the vortices had to come from the wingtips. And so Spedding, Dr. Spedding, drew curves on his data. You can see it right there. He drew curves on his data so that the vortices would come from the wingtips. Because the aero engineers kept saying, no, the vortices must come from the wingtips. And if he had drawn the line straight, he would have gotten the right answer. So I met with Professor Spedding. And he says, please call me Jeff. Jeff, what on earth were you thinking coming to Southern California? I mean, your whole career, you were the foremost bird researcher in all of Europe, perhaps in the whole world. And you hit the big reset button and you come to Southern California. Why on earth would you do that? And perfect British accent. Well, the surfing is better here, you know. The man's a surfer. And that's where he spends all his time looking at birds. When he's sitting out there just outside the surf line, he's watching the formation of pelicans going by, or the seagulls. But it never occurred to him that this was the answer to the whole thing. And it was the most amazing meeting. We went on for 2.5 hours talking about all the stuff each of us had done. And at the end of it, USC is now one of the 2 universities that uses this idea for calculating the load of the wing of birds. And they now use it for their aircraft design as well. Okay, I'm going to skip over these others. I have to talk about this one real quick. This is Stephen Portugal. We talked to him on the phone. He's the Royal Veterinary College of England. Got his PhD doing this work. He studied the northern ibis. And after getting hundreds of thousands of data points that show how much the birds like to fly wingtips overlap, he does his analysis with the wingtips lined up. And why would you do that? And so we went back and explained to him why you would want to change your analysis a little bit. And the birds actually do like to be overlapped, and here's the answer. And now Portugal does it our way. Now, if you take Portugal's data and you take the other 3 papers that have actually repeated this experiment, and you look at the sample size, and you normalize for the sample size, and then you normalize the birds for their wingspan. There's 3 different species on here. And you line up all the birds, okay, and you overlay everybody's data. You put the 0 point in the same place for everybody. You get that data. And you notice there's a green line on there that sweeps up. That's Prandtl's 1933 paper on what the upwash should be. And the blue line that humps over the top and then goes out to the right, that was the data that I calculated with my interns on what the upwash was outside of the wingtip. And you'll notice that when you lay that over the top of the bird data, all of a sudden everything lines up. The birds know exactly where the best upwash is. They know exactly where to fly because they can feel it. They know where it's easiest to fly. That's why birds do this. And all of a sudden, all this data makes sense. And it confirms everything we've done. One other thing. Why on earth don't they have that tip stall problem? Well, if you look carefully here, you'll notice that all the way out there at the wingtip, the lift goes to 0 right here. Not only that, you'll notice that the place where the wing would stall first is actually right here, not at the center line, but some ways out. And so if you ever saw a bird flying very slowly where it was right on the edge of stall, you might be able to see where the stall was starting, just outboard of the center line. Okay. This is obviously what birds are doing. People could have calculated all of this back in 1966. This is a gentleman named Noctegal doing his postdoc at Berkeley. And no one calculated this stuff. And so many times I would find people that walked right up to the edge, but they didn't finish the work. And I could never figure out why that was. And it drives me nuts, because this could have been solved 52 years ago, and you wouldn't be listening to me right now. And I apologize to all of you. You're stuck with me. And I am not all that smart, okay? I'm not a smart guy. I'm just asking a different question. Okay. So we built a series of airplanes, and Red Jensen, high marks to this guy for believing me. And so he built these things, started flying them, we instrumented them, we got good data off of them. And the thing was, he did all that even though there was not 1 second of flight data that proved this was right. Along the way, you'll notice the blue line down here on the lower right. When it goes up, the green line bumps up a little bit. The blue line is the roll rate. The green line is the yaw rate, and they go in the same direction. And this is called pro versus yaw. The red line that's on there that's bouncing around, that's the pitch rate. It was not a smooth day when we did this. By the way, this is the very first maneuver to ever measure this in flight. And this was on June 26th of 2013. Okay, we've repeated the data one other time. This is 2015, and we have 58 data points on here. I split the team into 2 different groups and had them solve the problem separately. The red line is what I predicted for this particular coefficient, and this is how much pro versus yaw you're getting for a certain aileron input. That's what this coefficient is. And the 2 teams, the blue team and the green team, they were led by 2 different young men, and they came up with 2 different results. It turns out that there's a subtle difference in the way they did the analysis that resulted in the 2 answers being slightly different. Engineering is not necessarily an exact science. There's uncertainty out there in almost everything we do. We have a wind tunnel test, NASA Langley. This was 2 years ago. We've also got an idea to try and land one of these on Mars. If you want to come over and see the little Mars airplane that we're playing with right now, come on over to the booth. We want to deploy out of a CubeSat. We're going to fit this thing inside of a 3U CubeSat, and as one of the other rovers is being inserted on Mars, we would have them throw the CubeSat out, and then we'd deploy the airplane at about 12,000 feet above the ground. We'd get about 3 minutes of data before we ran into the ground. By the way, paper airplanes on Mars fly at airliner kinds of speeds, okay? There just is not very much air on Mars. It turns out that if you ask a different question for propellers, you end up in a different place. We actually did this. The one thing that we were really surprised at, we knew that we'd get the same amount of thrust with less torque. That wasn't a surprise. What was a surprise was how quiet it was. And we had to go back and think about this, and talking with Justin was the one that made the observation first, and Red, we're sitting there and talking with Derek and in the lab, and it turns out that if you unload the tip, all the noise comes from the tip. And so you want to actually reduce the angle of attack at the tip of the prong in order to reduce the torque. You don't want the lift to carry all the way out to the tip. By the way, all of this work was done with interns. You're going to have to listen to one of my former interns here in a little bit. Stephanie Valkoff's going to come up here and talk about some of the UAS work she's been doing since she left my team. And Actually, she's in that lower right picture. And I've had many other teams along the way over the years. I have 2 more students that are showing up in 2 weeks, and that's going to be the spring team, and then I'm going to have a large group this summer. And there's one more paper that we're finishing up, and I want to, in case you guys didn't know, having a sense of humor is actually a very, very good thing. And Red's actually very good at that. So you have 3 choices. You can drag a vertical tail around with you all the time. By the way, do you know what a 737 tail weighs? It's about 8,000 pounds. That's 8,000 pounds of fuel you could have carried, 8,000 pounds of payload, 8,000 pounds of luggage or whatever. You can manipulate drag at the wingtips to control yaw. Look at that picture of the B-2. You notice how the wingtips look fat? The reason is they've got their elevons split open in order to create drag. Why would you create a flying wing in order to save energy and then create drag while you're cruising? Or you can do what birds do and manipulate thrust at your wingtips to control yaw. And oh, by the way, the wings get 12.5% more performance than an elliptical wing for the same mass of the vehicle. Okay. By the way, look at those pterosaur bones. How much load do you think they carry out there at wingtips? So total efficiency increases almost 70%, 70%. That's the difference between flying the way birds fly and what we do. Now, that's only a one-dimensional analysis. One of the things we've found out is that that large increase only happens at a particular point. It falls off as you get further away from that particular design point. Below that of the current approach, I should add. Okay, the current approach, if you have a fixed wing where you can't change the wing, then, and if you're trying to cruise at different design points, then it really is perhaps more advantageous to go back to the old design and use the elliptical load. However, if we had camber changing flaps, we could change the design point and get that efficiency increase over a broad range. So this is the airplane we're flying right now. We had a fiber optic shape sensing system, and you can see the fiber optics in the right, lower right. We also put pressure caps in the airplane, and one of the things we came up with is that there's a little tiny box. It's about a foot long and maybe 6 inches wide and about 4 inches thick, and it measures 100 pressure ports at a time. Have you ever stopped to think about, it weighs 2 pounds, by the way. It's not like it's made out of lead or anything, but this 2-pound box, no one has ever measured the pressure distribution on a paraglider. No one has ever measured the pressure distribution of a hang glider in flight. No one has ever measured the pressure distribution of a skydiver with a wingsuit. And suddenly all those things are possible with this little box around. And I remember the day that the students first put it all together, and I'm standing here holding this thing, and I'm thinking about all this. I'm going, we have a lot of work to do. So I have a friend, his name is Eric Chase. Eric decided somebody had to build a big one. Yeah, people flying. It was the most mind-blowing. I don't design airplanes, okay? I don't. And you have to imagine the guy hooking up the tow line, and they've flown it a couple of times, and I'm standing in front of the glider. I'm going, Steve Davey is the test pilot. And I go, Steve, you're sure this is okay? And he's going, yeah, it's fine. We've done this. It's okay. And you're sure? You're sure? And Eric is tightening the tow rope with the truck, and he goes, Al, get out of the way. This is flight number 8. There is an entire armada of vehicles following this glider as this is happening. He's under tow. There's a pickup truck over there on the extreme right edge. 600 feet of line in between. This was the last flight of the day. You'll notice there's a little bit of turbulence bouncing around. He's already at a couple hundred feet here. He's not wearing a parachute. Steve, what is wrong with you? Questions?
Yes, I noticed the front wheel, it's turning counterclockwise.
Yeah, it's like it's rotating backwards,
I
right?
would expect it to turn the other way.
No, if you stop and think about where the flow's being accelerated because of the upwash near the leading edge of the wing, it actually makes sense that it would be rotating backwards.
All right.
It really is. We had a couple of questions over here. Yes, sir.
Yes, is he going to drop the tow line and get down someday?
He does. By the way, Red is always complaining that I don't put spoilers on my airplanes. And I keep explaining, Red, I designed them to stay up. Anybody can go down.
Okay.
Yeah.
Is this El Mirage Drive?
Pardon me?
Is this El Mirage Drive?
Yes, it is. Yeah, you'll notice there are no NASA logos here or anything. This is sort of, we refer to ourselves sometimes as the garage band. He's already released here. He's testing out the speed brake. This is the first time we tried the speed brake, and it comes downhill pretty fast. He almost lands on the tow line here, and he has to pull up right at the last second and delay his touchdown just a moment. And then once the tow line's clear, he goes ahead and sets it down. All right, I've run over on my time. No more questions. Yes, sir.
Thank you. I was surprised not to see more modeling and simulation involved in the determination of the design. Why the reliance so much on experimental methods?
Good question. So, we are the Flight Research Center for NASA. We did not have access to a wind tunnel. No one was willing to give us any wind tunnel time. No one was willing to give us any money so that we could get wind tunnel time. The entire cost to getting that first data point, and oh, by the way, we published the paper eventually. It's a NASA technical paper. I have a few with me. There was just nothing that no one was willing to give us anything like that. And so until you have a successful solution, no one's willing to bet on you. Well, I got somebody to give me $2,000. And the first data results that were in here ended up costing you, the taxpayer, $1,651.17. That was the total delta cost in order to get the data for this report. So, but I had to steal the intern process at our place in order to do it. And we were getting interns, we needed something for them to do. Hey, I can do that. All right, thank you folks very much for your time.